Hey guys, today we're going to look at two different problems that discuss vapor pressure and boiling points. We'll get back to PV equals nRT and use that kind of strategically. And then we're also going to introduce what's called the Clausius-Clapeyron equation in order to discuss vapor pressure at varying temperatures. So let's dive right in. In this first problem, we are presented with dichloromethane, commonly abbreviated as DCM, pretty popular organic solvent. Its formula is CH2Cl2. We're told that it has a vapor pressure of 353 millimeters mercury, 20 degrees Celsius. We're also told that we have 55 grams of this material in a sealed 18-liter flask. And the question is, will any liquid dichloromethane remain in the flask once it's had an opportunity to vaporize, right? So at 20 degrees Celsius, will we be able to essentially meet the vapor pressure through the vaporization process, and will there be any liquid that remains? Okay, we're asked to show some calculations and ultimately justify our answers. So we use our calculations and then we defend those and really kind of state yes or no, right? So I think the question is the following. Do we have enough material, right? Is the quantity of dichloromethane enough on a mole basis in order to get the pressure to 353? And in particular, we want to essentially be able to get the pressure over 353, because what that means is that we would have some liquid then that condenses and that would be sitting in the bottom of our sealed flask. So again, as far as this concept of equilibrium vapor pressure goes, we'll have our liquid in our sealed container. This is a state of dynamic equilibrium where, the rate of vaporization or evaporation is going to be constant at a particular temperature, but as the vapor phase kind of builds up, the rate of condensation will increase, and the rate of condensation will increase until it matches the rate of evaporation. Okay, so again, we wouldn't really notice any change in the volume, nor of the pressure, because we would have reached that equilibrium pressure. So I think we'd maybe start with trying to figure out, well, how many moles of dichloromethane do we have in the first place? And that's pretty straightforward, right? We're presented with our formula. We use our periodic table to come up with our molar mass for the DCM, for the dichloromethane. We know that's the mass in grams per 1 mole. We're told with 55 grams, so I cross multiply and solve for 0.648 moles of dichloromethane. That is the actual quantity we have in our sealed 18-liter flask. So I think strategically there's two ways to approach this, okay? The first would be, well, okay, how many moles are actually required to get to 353? Because if we know how many moles are required, if we have more, then we'd be good to go, right? We'd have a saturated airspace and we would have, presumably reached our vapor pressure. So that's where we're going to start. How many moles are required to get to 353 millimeters mercury? So I go back to our PV equals nRT. I rearrange that to solve for my number of moles. You have to remember to convert the 353 over to atmospheres, given that we're using the following gas constant. To do that, those millimeters of mercury, we just divide by 760 to get to ATM. Again, we're presented with our liter value from the problem. I've converted my 20 degrees Celsius to Kelvin simply by adding 273. And I come up with 0.348 moles of dichloromethane would be required to reach this particular pressure, okay? And so what this means is that, yes, absolutely, because we have 0.648 moles of dichloromethane, we would have found that we have enough of the dichloromethane in order to vaporize, right? That's the amount of vapor that's required to reach that specific vapor pressure at the 20 degrees Celsius. So we would have, something like 0.3 moles of DCM left over. And so again, you'll notice I've answered the question that yes, there will still be liquid left in the flask because the amount that I have is more than the amount that is required to actually be in the vapor state to reach that vapor pressure. Okay, so we'd be good to go there. I think the second strategy would just be to ask yourself, okay, well, what happens if I were to actually vaporize all of the moles of dichloromethane I have? What pressure would I be able to reach, right? And if it's over the 353 millimeters of mercury, then I know I'm good to go. Okay, so again, PV equals nRT. This time what I've done is I've kind of arranged and solved for the pressure to be solved for. I plug in my values. Again, all of my moles, I've used the appropriate gas law constant, 293 for the Kelvin, 18 liters, good to go. In my final step, I know that I've solved for ATM, given my units of the gas law constant, so I've merely multiplied, in this case, by 760 to get to 658 millimeters of mercury. So what that means is that if all of the moles of dichloromethane were able to vaporize, we'd get to this pressure, which far exceeds what I know to be true about the vapor pressure at 20 degrees Celsius. So yes, plenty of liquid would still be present, because we would never get to this pressure, right? We'd get to that 353, and then the rate of condensation would match the rate of vaporization. We wouldn't be able to produce any more vapor at that point, and we'd have certainly liquid being retained in the bottom of the sealed flask there. Okay, let's take a look at a second problem. This one's actually a little bit more straightforward. It's honestly more of kind of the plug and chug type variety. Given kind of a set of data points, we're being asked to solve, for some unknown information. So imagine that, you and your esteemed lab colleague, you travel to the top of Mount Everest, where we know that the atmospheric pressure, or the external pressure, is only 228 millimeters of mercury. So again, pressure is very, very low up there at 29,000 feet. And we're being asked to calculate the boiling point, or the boiling temperature of water, if we were to be at that summit, okay? And there's a couple things to kind of keep in mind, but before we get there, what we're shown here is the Clausius-Clapeyron equation, which basically allows us to calculate either the pressure or the temperature of a gas using two sets of data, right? So there's a P1 and its associated T1, the pressure at a temperature, and what the vapor pressure would be for a substance, say the second vapor pressure, at a second temperature, okay? So we have to kind of remember what it means to be able to boil, right? That's what we're trying to solve for, is the boiling temperature. And so in order for water to boil, we know that the vapor pressure has to equal the external pressure. And the external pressure is just the atmospheric pressure. It's the 228 millimeters of mercury. So essentially what we're asking is, what is the temperature where the vapor pressure for water is going to be 228 millimeters of mercury, okay? And so again, you're presented with this equation. You might be wondering, well, okay, like I know that maybe this is my pressure 1, or maybe my pressure 2. It's kind of arbitrary how we define that. I'm trying to solve for that associated temperature. Well, what is the other missing piece of data? And I think what you have to realize is that we always have just the boiling point of water, the normal boiling point of water, kind of in our back pocket, right? We know that at 1 atmosphere, or 760 millimeters of mercury, that the boiling point of water is 100 degrees Celsius, or 373 Kelvin. So this will actually constitute, one of our data points. Okay, that the vapor pressure of water is going to be 760 millimeters of mercury at 373 Kelvin. And so presented with a second, vapor pressure that we need to be able to kind of, solve for, not solve for, but we'll be able to solve for the necessary amount of energy reflected as temperature in order to get to just 228 millimeters of mercury for that vapor pressure. So I merely plug in my values into the top equation here. In order to solve this, I'm going to simplify, and I'm going to take the natural log of the 760 over 228. I'll also simplify the 42,700 divided by the 8.314. You'll notice that we have a different gas law constant this time around, given that we're using units of joules. So rather than the 0.08206, I instead have to default to the 8.314, given that that's the gas law constant that uses energy, okay? At this point, I bring the 5135 over. I'm going to bring the 373 times T2 over as well. I'll add T2 to this side in order to combine like terms. I divide the 373 divided by 1.08, and I get a final temperature of 343 Kelvin, or 70 degrees Celsius. okay? And that's what we'd expect, right? If we're only trying to get to a vapor pressure of 228 millimeters of mercury, as opposed to, say, 760 millimeters of mercury, we know that if you have to get water up to 100 degrees Celsius in order to get to this vapor pressure, well, if we are trying to get less vapor, right, less quantity, less moles of gas in order to get to that pressure, you would expect that we would need less energy, and therefore the boiling point at a lower external pressure, atmospheric pressure, would be less than the 100 degrees Celsius we're more common, we more commonly see, I should say. All right, thanks for tuning in, guys. Hopefully that's a good start on some of the things that we can encounter in dealing with vapor pressure and boiling points and some of their associated calculations. Thanks, guys.